Picture this. Hurricane Dorian is rapidly approaching the Gulf Coast. In a high-stakes scenario like this, the Emergency Operations Center needs answers, and they need them literally right now. Who is evacuating where, and who can still talk to whom? So welcome to Case Study 08, Sampling Big Networks. Before you dive into your 2 to 4 hour solo sprint this weekend, let's just take a few minutes to orient you to the exact engineering problem we're going to tackle.
Right, so during the actual Dorian crisis window, the evacuation flows produce this massive network of 316 Florida County subdivisions. And here's the immediate engineering roadblock you're going to hit. We're talking about over 33,000 weighted edges across 8-hour time slices. It's just a massive data hairball. Mathematically speaking, it's way too big to load fully into your laptop's memory, and it's definitely too large to query efficiently when every second counts in a crisis. You just cannot analyze every single node.
And that brings us directly to the core professional skill we're focusing on today, which is identify. We need to take all this messy, real-world relational data and deliberately frame it into a computable graph. Look, when a network is simply too massive to handle, you're forced to sample. You have to identify what actually makes the cut. You absolutely must decide what matters most for the system you're engineering, because, well, you simply can't keep it all.
Okay, let's slow down for a second. Before we get into it, before you even think about touching a single line of code or booting up the interactive lab, we are having a sketchpad moment. The real heavy lifting thinking in this course, it happens on paper first. The software is just there to verify your logic. So, out of the 40 coastal parishes we're looking at, I want you to literally draw just 5 of them on your physical notepad. Got 'em? Now, go ahead and heavily mark those 5 in mustard yellow ink.
Now, the absolutely crucial part here is predicting what happens next. Because when you ruthlessly reduce a 40-parish network down to just 5, things vanish. Right next to your drawing, I want you to jot down exactly what you expect to lose. I mean, are you creating massive geographic blind spots? Are you suddenly missing the structural triangles that actually prove communities are moving together? What about your degree estimates? Are they going to be completely hopelessly biased? Commit to these predictions on paper first.
All right, once that sketch is done, then you'll open up the interactive Gulf evacuation tool in your browser. And this is where it gets fun. You're going to adjust 4 very different sampling strategies: random node, ecocentric, snowball, and random edge. This whole exercise is designed to expose the ruthless trade-offs of sampling. You see, every strategy is a structural choice. Take ecocentric sampling. It's great at preserving local neighborhood structure, but it totally oversamples hubs. Or random edge sampling. It keeps your edge distributions nice and clean, but it can completely miss entire disconnected components of the network. You're going to resample live and literally watch these metrics warp in real time.
So as you move through the interactive learning checks in the tool, you'll be asked to set the sample size to 30%, cycle through the different strategies, and compare the fallout. For instance, you're going to have to answer this: which sampling strategy disproportionately destroys triangles? And there is absolutely no way I'm giving you the answer right now. You're going to have to figure that out for yourself by watching the network rebuild on your screen and really thinking through the probability of capturing connected edges.
Then, once you've built up that intuition in the interactive sandbox, we transition over to the code. Whether you prefer working in R or Python, the starter script is all ready to go. You'll load in the trimmed Florida evacuation data, compute the baseline stats across those time slices, and then apply 3 specific sampling strategies: egocentric, edgewise, and a spatial buffer specifically around Miami. Your ultimate goal here is to track the average edge weight over time. You want to see which strategy actually manages to preserve the real population's time series.
But before I let you go tackle this, there is one massive misconception we need to completely dismantle. A sample is not just a perfectly proportional, cute little miniature of the whole network. Sampling is never neutral. Actually, let's put it this way. You don't choose if you lose data. You choose what you lose. Your fundamental job as an engineer is to pick the specific bias that doesn't completely destroy the question you are trying to answer.
Okay, time to get to work. Close out this explainer, grab your pen, and open up that physical notebook. Here is your starting prompt. If you can only afford to measure 5 parishes during this evacuation, which 5 do you pick and what exactly are you willing to lose?